This is just quantum potato chip is just one. It's just a paper. Just a paper we wrote recently. This is just our mostly like served as an experiment.
Maybe bigger.
Mostly not just.
Can you zoom in on that quite a bit? The screen is quite small for us, so you need to zoom in.
I think I have a normal version.
Just make it full screen. There you go. That's good.
Okay, so this is like a not just computational experiment. A quantum computational experiment is also like an experiment of paper writing, because we were so used to writing computational essays. This is like a Stephen Wolfram way of talking about like how this kind of things has to be written. You write a computational, not just a paper with formulas and that, but you also include a bunch of code around it so that it becomes also instantaneously reproducible. So you can click on a formula, click on the graphics, everything that is in the paper should be readily available for reproduction, right? So and it's not very easily done in the conventional format like PDF, right? So we kind of tried to make it a PDF, but at least try to include the code as much as possible. So we wrote this paper. This is a simple paper about geometry of qubits, right? But we also included a bunch of source code at the end, just a bunch of Wolfram language code for each of the figure and most of the formulas, and it also comes with a notebook. Somewhere at the beginning there's a link. So this is just the appendix with all the relevant code for each equation and figure. But also there's a link somewhere at the beginning, I believe. And maybe it's an old version or whatever. Somewhere in the beginning there should be a link to this notebook. I just downloaded it, which also includes all the code in more detail with also some comments. So that's a a good experiment. We want to continue doing that. Maybe for some next paper we're gonna write. But particularly this paper was about, well, I guess I have to talk about what the paper was actually about. So this is the quantum experimental, this is the computational experiments about just geometry of qubits, basically explaining how qubit geometry looks like, not just in the conventional block space, which is, as you know, that like a qubit is some kind of block sphere. Like here, this is a good picture. I think this is like conventionally how qubits are represented. You have a block sphere, and the qubit is just a arrow pointing on a surface or inside of the ball, which represents all possible pure states and mixed states for a single qubit. But we were also exploring what does it mean for a qubit to be in the phase space and how you can probabilistically equivalently represent the same structure, the same usual state vector that is usually represented as a list of complex amplitudes. How can you also represent it as a list of probabilities or quasi-probabilities? Then we have like this nice analogies from one-dimensional. How can you represent a simplex, which is just a space of probabilities, right? You know that one-dimensional probability space, this is very small picture, but it's basically when you have this one-dimensional line that can represent a one-dimensional probability distribution, which is just a coin. So you can have a biased coin, which every biased coin is just located somewhere on this line. So exactly in the middle is a fair coin, which is like 50% tail, 50% heads, right? And the space of all of those coins is just one-dimensional probability space, which is one-dimensional simplex, and just a geometrical intuition for it so that you can rotate it and project it to one dimension. And you can, like this, right? This rotation. You can do it in one dimension higher, which is now a two-dimensional simplex. It's just a triangle. You can again rotate it about some axis and project it to two dimensions and so on. And you can do it for relevant dimension here for the qubit is four-dimensional, because when you project it, now you can't really similarly visualize the rotation itself, but you can visualize the final result is the tetrahedron, which is the projection of that four-dimensional probability space to 3D. So now you have a three-dimensional shape, which is a tetrahedron that corresponds to the projection of that four-dimensional probability space to 3D, right? And this is the kind of shape that we're gonna envelop our block sphere. And that's basically, we go through this construction of all those rotation operators and so forth, so on and so forth. And we basically have a picture like this, right? So as soon as you envelop our block sphere with the simplex, you can map every qubit to a probability vector. And now it's not even a quasi-probability representation of a qubit, which is maybe you already know from like Wigner representations, which are or Wigner quasi-distributions, which are usually known in quantum mechanics, not this quantum information theoretic results like for a single qubit, but for actual quantum mechanical systems when you have a continuous infinite dimensional phase spaces. But here it's a much smaller phase space, which is just this tetrahedron, and you can actually visualize the whole of the space and all of the points in that space. And you can so that each point is the qubit. And when you represent your qubit as a probability distribution, you can just you can visualize it inside of the tetrahedron. And the basic question we asked, because a qubit in because you can do this projection for a qubit, you can basically assign some probability coordinates to each of the quantum state. You can also think of it as a, because it's a phase space, right? Phase space is a pair of dual variables. Like in quantum mechanics, you have coordinate and momentum. For a qubit, which is a finite dimensional, finite dimensional discrete system, is the analog of dual variables would be two spin projections, like horizontal and vertical. And you can do the similar thing. Basically, you can decompose your phase space over these two variables, and you can ask whether they're independent or not, because now you have a equivalent probabilistic interpretation of the same space that represents a qubit. And that's basically where the potato chip emerges. You just ask a simple question: what would be the space, the probability space, when you assume that those two dual variables, those Fourier dual variables for a qubit, when they're independent of each other, right? And that's exactly what constructs this potato chip shape, which is like here it's a red outline. You have a bunch of other potato chips here, and even some layers. You can actually quantify it so that you can have more layers of chips. Basically, you can compute some classical probability metric, which is called Matthews correlation coefficient, and you can compute it for every qubit, and you can see that the potato chip with the zero correlation is that exactly the one in the middle, which gives you the space of all the qubits where those Fourier dual variables are completely independent in that particular basis. And we can ask a bunch of questions like that about this shape, so that as soon as we have this probabilistic interpretation for a single qubit, we can compute correlations. We can we have this nice layered construction of all the different basis representation for the same thing, because the outer tetrahedron that completely envelops the block sphere is that probabilistic interpretation, but there's smaller ones that reconstruct more familiar spaces, phase spaces for the same qubit, which is a quasi-probabilistic, where this would be the Wouters and Wigner representations. This is again the potato chip shape. This is how the classical, I guess, all the region that contains all the classical states. There's a notion of classical states for a qubit. You can also compute that and how it relates to that shape, which is just like some boundary on it. We also studied how it like phase space, how the channels act on that space. This is the usual channel processes acting on the whole space of qubits on an entire block sphere, right? It just modifies it in some way, morphs it into a different shape. And if you apply it to a quantum chip, those space where you assume that your phase space variables are independent, it also modifies it. And basically you can see that some channels just morph the chip so that it still lies in the same space, so that you can still, every point is still correspond to those independent variables. But some channels basically move that space away from it. So they're no longer, some points become no longer independent. So it correlates those. in this way. You can ask about some dynamical evolution of this shape. We can just simply ask, okay, if the shape, if this boundary of a chip is just some line, some trajectory along the Bloch sphere, which is exactly what happens when you, for example, evolve quantum state by some unitary evolution or some arbitrary Hamiltonian. Usually it's some trajectory on the Bloch sphere. If it's unitary, then it's some circle. Just but there's some more complicated evolutions you can think of, describing the trajectory of how your quantum state evolves. And we were just trying to ask, okay, if that shape, if you have a shape, is there some dynamical process like some Hamiltonian or in general some master equation or Liouvillean operator exists that exactly reproduces this trajectory? And we tried to reconstruct it, and it's almost, you can almost do it. Turns out it's a little bit unphysical. You can construct one, but turns out there's some negative like damping rates that you have to introduce. So it's a little bit unphysical, but at least mathematically you can do it. So and that's basically that was the paper. And the main point here is just it's just a physical exploration, but it also amplified with all of those computational reproduction experiments, so that you can actually run this code for every picture. If you have any questions, every formula and every equation is there in the notebook and reproducible by everyone else. So I guess at this point I'm finished. You can ask some questions.